This is part one of the series Limits, and it's actually the introduction to the general overall topic of integral and differential calculus. This is our entry into the actual subject of calculus. Now, before calculus, up to this point in your career, you have worked with static mathematics. You've done things in geometry like finding areas of rectangles, and you've looked at slopes of lines and evaluated functions at a specific x value, things of that nature. In calculus, we're interested in changing systems. We're looking at dynamic things. Calculus is the mathematics of change. And the reason for that, as the story goes, Isaac Newton in the 1600s was asked why the orbits of the planets were ellipses. And he took some time to contemplate the idea and came back describing that ellipses were conic sections, cross sections of cones. And he described them with this new mathematics he had to develop in order to describe the motions of the planets, and that was integral calculus. So its whole nature comes from dynamic changing systems and describe dynamic systems. So before you were dealing with evaluating functions at a point, in calculus we're going to determine what happens to functions as they approach a point. That's the idea of limits that we're going to talk about. You've looked at slopes of lines. In calculus we're going to determine slopes of tangent lines to curves. And we're going to find equations of tangent lines to curves. Things of that nature. So our studies are going to be related to the dynamics of a situation as opposed to static situations. Now, calculus is fundamentally characterized by two basic problems. The first one is the tangent line problem. In the tangent line problem, let's say that we have a secant line, that is a line that intersects a curve at 2 points. And we want to determine what is the slope of this line when it reaches a tangent line at this point. Well, it's easy to find the slope of the secant line. We simply use the slope formula, use this y coordinate, this x, and this x. But as this difference, this change in x here, approaches 0, as this point moves closer and closer, this secant line becomes closer and closer to a tangent line. Let's take a look at that situation dynamically. So here's an enlarged view of that same picture. And if I take this point and I move it towards my target C value, you'll notice that the secant line is becoming closer and closer to a tangent line. And as I come directly over the top of this point where delta x becomes 0, the distance between C and C plus delta x, it becomes a tangent line. So that's the idea of the tangent line problem, that we have some value of C on our x-axis, and we want to find the equation of a tangent line, or the slope of a tangent line at a particular point, which is the point of tangency of that line to the curve. And that's the nature of the tangent line problem. Now, the second fundamental problem that we have is called the area problem. Now, with the area problem, what we're interested in is finding the area under a specific curve between any boundary points. So we're looking for the area under that curve. Now, as you can detect from the picture, what we're going to try and do is we're going to try and approximate the area by using the areas of rectangles underneath this curve. And let's take a look at this situation in a more dynamic environment. So here we have the same picture. Now, you can see here that we have some gaps. With these rectangles taken as they are, we have some gaps. But you can also see that if I increase the number of rectangles, it decreases the number of gaps. And so theoretically then, if we were to increase the number of rectangles to an infinite number, then we should get an accurate representation of the area under this curve. Now, notice what happened to the width of each one of these rectangles as we increase the number. As you increase the number, the width of each rectangle gets smaller and smaller. Again, we have this idea of approaching a specific value, which is the idea of limits. So we're going to be interested in what happens when we sum the areas of these rectangles as the width of each rectangle approaches zero width, or alternatively, as we look at the number of rectangles increases to infinity. We're going to look at those conditions. So in both of these cases, we're dealing with the idea of limits. In the case of the tangent line problem, we were interested in what happens as this delta x value approaches zero, and in the area problem, we're looking at what happens when the width of each one of these rectangles approaches zero. That idea of what happens to a system when a particular value approaches a number is the central idea behind limits. So let's start with our discussion of limits. To start with, let's take a look at a very high level general definition of limit. This is by no means a formal definition. We're going to deal with that later. But in general, a limit is a value that a function approaches but doesn't necessarily reach as the value of the independent variable becomes arbitrarily close to a specific number, or as it approaches infinity, positively or negatively. So that's a very general description of a limit. So let's explore this in greater detail. Let's say that you were asked to describe this function. What would you say? Well, to take a look at this function, you would probably sit down and use some of your pre-calculus skills and notice that this is the difference of two squares. So you would break down the numerator by saying this is x plus 2 and x minus 2 divided by x minus 2. And you would notice that this is a problem. The function doesn't exist at 2, but because this x minus 2 factors up here, these two cancel out. So you would know that this function is the equivalent of the equation y equals x plus 2, but at x equals 2, it has a hole. So let's take a look at that graph. Now this would be the graph of your function. You would see that it's a straight line and it has a hole right here. So the only difference between this and this is that this expression doesn't exist at this value. So that's the idea. That's probably what you would say. But what if I were to ask, what value does this function approach, or what is the value of this function at x equals 2? You would say it doesn't exist. But I'm interested in the behavior of the function. What is the function approaching as the x value approaches 2? Either from the negative side, from the left here, or from the positive side, from the right, starting higher and coming down towards 2. Well, the easiest way to do that would be to plug some values in to the function and see what they come out to, and see if we can develop a pattern here. Now I've put in this little table of values down here, and I put in some arbitrary numbers, and I want to see what's happening to this function as it approaches 2 from the left-hand side, that is from values less than 2, and gets closer and closer to 2, and what happens when it comes in greater than 2 and gets closer and closer to 2 from the right-hand side, that is from numbers greater than 2. So let's take a look at what happens with this function. We'll pull up our calculator. I've gone ahead and entered my function, so you can see that my function is inside the system. I've changed the calculator to be in ask mode for the independent variable. So I go to my table and I'm going to start typing in values to find out what the value of this expression is at these different values. So let's start with 1.75. The value comes out to be 3.75. Now let's try 1.9. 1.9. And now we're at 3.9. Let's try 1.99. And while we're here, 1.999. So you can see that we got 3.99 and 3.999. So it's 3.99, 3.999. Now let's do the same thing from the right-hand side. Let's type in 2.25, which gives us 4.25. Let's do 2.1. We get 4.1. Let's do 2.01. That's 4.01. Let's do 2.001. And we get 4.001. So we had 4.01 and 4.001. Now I think you can see fairly clearly that from the right it's approaching 4, and from the left it appears to be approaching 4 as well. So from an analytical standpoint or a numerical standpoint, we would say that the limit of this function as x approaches 2 is 4. And the way we would write that is we would say the limit as x approaches 2 of x squared minus 4 over x minus 2 equals 4. That's not saying that f of x equals 4 at that point. It's saying that this function is approaching 4 at that point. That's the key for limits. We are not dealing with what is the value actually at the function at that x value. We're asking what is it approaching at that value, because this function doesn't exist at 2. So the question of what is this function, what's the function's value at 2 is meaningless because it's undefined. That's where limits come in. They're talking about the behavior of the function, not what is the actual value at that particular x value. Okay, so let's try this with another problem. So in this problem we're going to do something very similar. We're going to evaluate this function at various values of x and find out what value this function is approaching as x approaches 0 from the left and from the right. So do the same thing. What I would suggest is build a value table. Pause the video, go ahead and build your value table, and when you get it built, start the video back up again and see if yours matches mine. Alright, now if you didn't get these numbers, it doesn't really matter. The issue is we just want to find numbers that are close to 0. And so I just picked logical numbers here that are approaching it from the right and from the left. Now go ahead and plug these into a calculator, fill in your table, and then let's see if we match when we come up with the value this function is approaching. So from the left, I started at a 1.866 and got closer and closer to 2 from the left, and started at 2.118 and got closer and closer to 2 from the right. So I would say that the limit as x approaches 0 of x over the square root of x plus 1 minus 1 equals 2. That means that as x approaches 0 from the left and from the right, the function is approaching 2. Doesn't mean it equals 2, it means it's approaching 2. Let's take a look at one more problem just to solidify this idea. Here we have a piecewise function. We want to find the limit as this function approaches 2. Now we can see here that for all values of x that aren't 2, the function is 1. So from the right, it's approaching 1. From the left, it's approaching 1. It makes no difference what the function is at 2. Limits are only concerned about what the value of the function is as it approaches that target value. So we would say the limit of this function as x approaches 2 is 1. We'll continue these ideas in the next video. So I'll talk to you then.